Hello everybody, we're going to finish the second half of module 13 today. Page 436 in your textbook. We're going to start with energy diagrams. You will have to determine if a diagram represents an exothermic reaction or an endothermic reaction, and also be able to calculate the change in enthalpy by reading the diagram. Let's look at the first example. This is similar to what you have on page 436. It represents an exothermic reaction. In the y-axis, you have the amount of energy in kilojoules. This represents time, so it's the reaction progression as it moves on. You start with reactants, A and B, and you produce product. Here is represented with a C. So as you start, you see that it has a bump, and then it falls down, and then it's flat again. Okay? As the progression of the reaction goes on, the energy levels out. Anytime that your reactants are at a higher energy than the product you produce, remember that if you go this way, this represents energy, so this is higher than down here. So if your reactants are higher than your product, when you finish, that product has less energy, you have an exothermic reaction. Energy has been lost in the form of heat usually. Okay? But as you see here, you seem to have a bump here. It's like the energy goes up and then it falls. This amount of energy before it starts falling again is called activation energy. All reactions, all of them, require some kind of activation energy. Some require more, some require less, and we'll see in a minute another diagram that shows that. But you need to give energy to the reaction to get started. It can be from the environment, just from the air, the heat from the air, or by turning on a match underneath the reaction, so in the form of a flame. The top, another term you need to be familiar with, is the top of this activation energy hill is called the intermediate state or the activated complex. Basically, all the atoms of the reactants have come apart. Remember that to break apart bonds, you need to give energy, the activation energy, and then they rearrange themselves again to create a product. The difference between the level where the reactants start and the level where the products end, is your change of enthalpy. It's the energy release, and by reading the amounts, the beginning and the end, you can calculate the amount of energy that was released, and you're going to learn how to do that. So here is another one. Let's talk about activation energy. As you see here are your reactants. The product ends right here, and each one of these reactions, 1, 2, and 3, has different bumps. Remember that any bump that is higher than the reactants represents the activation energy, the amount of energy you had to give to the reaction to get started. This bump is smaller than this one right here, and this one is smaller than the one right here. So that means that the blue one, this reaction represented by the blue color right here, require less energy than the one represented here with the peach color. And the pink one requires a lot more energy to get started, more activation energy. And you need to be able to do that. You need to be able to tell me which one of different reactions represented by energy diagrams are using more activation energy by looking at which one has the bigger bump. That's all it is. Okay? So here it is. All chemical reactions have an activation energy. In order for the molecules in a chemical reaction to get close enough to rearrange their electrons, because that's what it is, a reaction is just those electrons being shared or given away or taken or whatever, they must be given enough energy to overcome the repulsion that their electrons feel from each other. Each reaction has its own unique activation energy, and you need to know that. Now, figure 13.3 on page 438 represents an endothermic reaction. Let's look at it. Here you start with your reactants. You always start with your reactants. The products are right here. You have your energy on the Y and the progression of the reaction time or reaction coordinate. Okay? So what do you notice here? The reactants at a lower energy level than the products. What does that mean? Those reactants gain energy to end up here. So you have some activation energy to get started. You reach the activated complex, so those atoms are broken apart, and then it goes down, releasing some energy, and here are your products. But as you see here, from where they were to where they end, they gain some energy. That's your enthalpy. So you can go to the side, usually they have numbers here, and you can read the difference right here, how much energy. Endothermic means that they are taking in energy, so how much energy it took in to proceed to create the product. Let's look at another example. So in some of the problems, they're going to be giving you problems like these. They're going to show you different diagrams, and you're going to have to decide, is this an exothermic or an endothermic reaction? And the only way for you to do that is to notice the differences, okay? So to read the diagram, remember that in endothermic reactions, the reactants, when you have reactants, are always at a lower energy level than the products. In exothermic reactions, the energy of the reactants is higher than the energy of the products. This is the enthalpy, energy absorbed, endothermic reaction. This is the difference in energy between the reactants and the products, is energy release, enthalpy for the exothermic reaction. All of them have an activation energy that needs to be reached before the reaction proceeds, activation energy, and they all reach the activation complex, the top, where all the atoms are broken apart, because you need to give energy to break them and then more energy to pull them back. When you break them apart, you give energy, and when they get back together and form the product, they will release energy. Just depends on who wins. It's going to be exothermic or endothermic. We covered that last week. Okay, what else do you need to be able to do? Well, here's an example. Example 13.5 on page 438, and then we're going to do some more. Says, these are not very good drawings. I had to draw it with my mouse, but they represent what you have on page 438. So look at your book for the real picture. It says, consider the following energy diagrams. 3 questions. Which one is the most exothermic, and what is the change of enthalpy in that one? Which one is the easiest reaction to start, and which is exothermic? Okay, it should say endothermic. I just changed it to endothermic right here. Okay, so which one is the endothermic, and what is the change in enthalpy in that one? So let's look at the diagrams. So let's look at the first one. The first one, here are your reactants, here are your products. Reactants higher than the products, it lost energy. This is exothermic. Okay, we have an exothermic here. We have another exothermic. This one also has the reactants higher than the product. This is also an exothermic reaction. So we have 2 exothermic reactions. Question is, which one is the most exothermic? That means the one that released the most energy. Let's read the amount of energy released. 100 and this one is almost 50. So let's say that this lost about 50 kilojoules of energy. What about this one? Here are your reactants, here's your product. The difference between 50 and about 25 is 25. So this one lost about 25 kilojoules of energy. So this one right here is the most exothermic, and the change of enthalpy is minus 50 kilojoules. First one is done. Which one is endothermic? Well, this one is the endothermic because the reactants start lower than the products. That's where the products go. And they want to know what's the change of enthalpy. Well, read it. From 20 to about 40. So that's a change of 20 kilojoules. Being endothermic means that it's positive 20 kilojoules of energy. So C is also answered. The last section says, which is the easiest reaction to start? For a reaction to be easy to start, that means the activation energy is the lowest because it requires less energy to get started. So we need to look at the bombs here. So when you read easiest reaction, they're talking about activation energy. Easiest means the less activation energy required. If it would say harder, which is harder to start, you look also at the activation energy, but you look for the highest bomb. It would require more energy. So of the three, which one is the one with the smallest bomb? And your book is more clear than in my pictures right here. 3, okay? This diagram number 3 is the one that has the smallest bomb, representing activation energy, and that means requires less energy to get started. Let's do extra practice problem number 2 and number 3. You're going to find them on page 581 in your textbook. So let's move on. Make it it's going to be hard for me to draw this, but let's start with number 2. It says, which of the following diagrams indicates an endothermic reaction, and what is the change of enthalpy of that reaction? See if I can draw it a tiny bit with my mouse. It's hard, but I'm gonna try. So let's go to the whiteboard, which is black. There you go. And let's see. Get some white. You have 2 diagrams. Oh well, this is going to be a lot easier than I thought. One looks like this, number 1, and number 2 looks like, I mean, it's not perfect, okay, people. This is a mouse I'm using, like this. So they want you to identify which one is endothermic. Remember to be endothermic. The reaction, the reactants will have less energy than the products. Here are your reactants, here are your products. So number 2, okay, is an endothermic reaction. In this case, you had your reactants here, your products here. To go here, they lost energy. From here to here, they gain energy. I hope everybody can see that. The second section of this question says, what is the change of enthalpy? What's the change of enthalpy? Well, you go to the side and you start reading. You read what's here, what number is that? More or less like 18 or something like that. More or less 18, let's say that. And here are the products. If you read the number right here, is about 70, maybe, about 70. So the book says this is 15, but it's hard to read. These diagrams are not very good, so anything that is close to that number will be fine. So you're gonna do 70 minus the 15 or 18, whatever you decide the number is, and basically let's see what units they're using. They're using kilocalories, so be careful with that. You have to use the right unit. It's about 55 kilocalories of energy. That's a change of enthalpy, and it's positive because is an endothermic reaction. So this is your answer. So it varies a tiny bit depending on what you read right here, how you decide this number is going to be. Okay, this is number 2. And the other one I wanted you to do was, says number 3 says, for the diagram above, those two diagrams again, which represents the reaction with the lowest activation energy. And remember that activation energy means the bump that allows this reaction to go on. So we need to read, let me see, so basically this bump that before you reach the activated complex right here. So read this and read this right here. What is the difference between the amount of energy when you start and at the top? So if you read here, this is between, once again, you're going to have to kind of guess. This is between, I don't know, 50, 75, maybe 90 and 100, so it's about 10 kilocalories. And if you read right here, it will be between the 15 or 18 you decided all the way to 70. So basically, it was obvious that this was a bigger bomb, so you would have thought, oh yes, this one is the one that requires more energy, so this one is easier to get started. But be careful, read the numbers too, because sometimes they try to trick you. The numbers are not, the scale is not the same on both graphs. In this case, they are not. So to read the amounts on the side. Lowest activation energy is a little bomb, so could have 1. This one right here is your answer. Okay, there you go. If this doesn't make sense, please do ask questions when we talk during our Zoom meeting on Friday. Let's go back. Okay, page 439. A new concept for you: the second law of thermodynamics. Before we go into what this law says, we need to understand what entropy is. Entropy, represented by letter capital S, is a measure of the disorder that exists in a system. So if things are very well organized, we say that the entropy is small. If it's very disorganized, because it's disorder, there's more entropy. And things tend to get disorganized in nature. This change tends to be spontaneous. Something goes from more organized to less organized, or more chaotic, or more disorderly. This is a spontaneous event. Same thing over here. This is not a very probable way for the bricks to fall when they fall. This is a more normal way for the bricks to fall. Disorder. The second law of thermodynamics states the entropy, and remember, entropy is just disorder, chaos, whatever you want to call it, of the universe must always either increase or remain the same. It can never decrease. And here it is mathematically. The change of entropy in the universe is always more or equal to 0. So for things to be spontaneous in a way, entropy needs to remain the same or increase. It never decreases. And you may think, wait a minute, I know things that seem to be getting more orderly. For example, freezing of the water. You go from liquid, which has more energy, molecules are moving more than in a solid, and they become solid. So why? That seems to be breaking the law of the second law of thermodynamics. Well, because you need to consider not only the water, but the whole system, everything around it. So while water freezing below 0 decreases the entropy of the system, so the water itself is becoming more organized, less chaotic, okay? The heat given off to the surroundings, remember, it's losing energy in the form of heat. It goes into the air. And that increases the entropy of those surroundings to a greater extent. So the universe as a whole, the entropy that's happened there is positive. So that process is spontaneous. You have to take into consideration the whole system, not just the small part of the system where the water was freezing. That energy went into the air, the molecules of air got energy, and overall there was more chaos for that system. So it's spontaneous. Now, page 441. General rules of entropy. You need to know them, not just the definition, but you need to know how it works. Number one, entropy of a substance, so the chaos, disorder, whatever you want to call it, changes when the substance changes phases. The solid state has the least amount of entropy. The liquid state's entropy is higher than the solid state, but less than the gas state. The entropy of the gaseous state is the highest of them all. The entropy of a system increases with increasing temperature. The entropy of a system increases as the matter it contains increases. So here you go. When you have a solid, you already know that everything vibrates. There's movement in all of them. But in a solid, the movement is small. Those particles that form part of that solid are organized, and there's not a lot of chaos. So the entropy is smaller than if it was in a liquid state. These have more energy, they're moving around. It's a liquid, it's fluid. But the entropy, the disorder in a liquid, is smaller than that you would find in the gas form of that substance. Those atoms, molecules, whatever is making up that gas has more energy, they're moving around, colliding with one another, colliding with a container if they're in a container. So there's more chaos in here. But not only that, if you have liquids and you're comparing two liquids, whichever has the most molecules, most matter, okay, is the one that has more chaos in it. Just think about it. If your room only has a bed and a side table, there's not much you can do to make a mess out of things. The more things you put in that room, the more mess it can get. It's the same idea. Okay? Now, the first thing we're going to have to be able to do for this section of the module is to identify the sign for entropy. Is it positive or is it negative? Going from a lower to higher disorder is going to have a positive value. So we say that the change in entropy for that system is a positive. So if you go from lower, so more organized, to more chaos, positive entropy. Going from a higher disorder to a lower disorder, we say that it's losing chaos, so the entropy is negative. Okay? But what about chemical reactions? To determine what's going on in the reaction, we're going to look at this. Look at the number of molecules or atoms on either side of the equation. So remember that they can be moles, those numbers, those stoichiometric coefficients can be moles, but a long time ago we also talked about the fact that they also represent molecules. So let's see which one has the most. The reactant side or the product side. And then look also at the phase of the substances involved. Are they gas, liquid, or solid? Gas always beats liquid. Liquid always beats solid when it comes to chaos. So here are the rules. The side of the reaction that contains the most molecules or atoms in the gas phase has the highest entropy. That's the one that's going to have more disorder. If no gases are present, then the side that has the most molecules or atoms in the liquid or aqueous, meaning in water, phase has the highest entropy. And finally, if all substances are solids, then the side with the largest number of molecules has the highest entropy. So you need to know this because you need to be able to apply it. How? Let's look at this. Page 442 in your textbook, and then we're going to do one on your own. For each reaction below, determine the sign of the entropy. Well, let's look at all of it. Solid, aqueous, and gas. Solid is the least. Aqueous has some. Here we have aqueous too, and then we have a gas. Any side that has gases, if the other side doesn't have a gas, this one always beats. The presence of a gas always beats not having a gas on the other side. So this one right here, we're going to say that this one has gone from less cows to more cows. So the change in entropy is a positive one for reaction A. Okay? So let's look at the second one. That's all you're doing is looking and saying, okay, do we have gases? Do we have liquids? If it's not there, then who has the most matter? We have a gas and a gas and a gas. Everybody's a gas. Everybody has chaos. But which one has the most? Which side? Well, here's 1 and 3 is 4. And here there's only 2. The side that has the most matter wins. So this one went from more chaos to less chaos. So here, the change of entropy is going to be negative. Let's look at the last one. We have a solid, we have a solid, we have aqueous, and a liquid. Solid is the least chaotic. We have liquids and aqueous right here. So we know that this side right here has more entropy than the solid reactants. So you went from less to more. That means that the entropy here is positive as well. Let's try on page 581, practice problem number 5. You have the same kind of, let me go to the whiteboard, same kind of thinking, okay, going on. What is the sign? We're going to just do it together, number 5. So what is the sign of the entropy for the different reactions? Is it positive or negative? Are they gaining chaos or losing chaos? I'm going to do A, and I'm just going to put, I'm not going to write it down because that would take too long. Aqueous, liquid, gas, and then it becomes aqueous plus another aqueous. Okay, let's look at these. Aqueous kind of cancel each other, okay? Then a liquid. Okay, this is more organized than gas, but here's a gas. Oh, okay, so this is really chaotic. So basically this went from chaos to less chaos. What does that mean? That the change in entropy here was negative. That's what it means. Okay, it went from more to less, and that's a loss of chaos. So it has a negative sign. Let's look at B. On B we have a solid and then a liquid to become a solid and a gas. Gas always means more, so it went from less to more. So the change of entropy here is positive. Okay. C. We have a gas, another gas, and then it became a gas. Oh, and another gas. Everybody's a gas here. So the next thing we need to do is to see which side has the most matter. So let's look at the numbers. We have 4 and 5 and 4 and 6. So here we have 9 and here we have 10. So went from less to more. So what does that mean for the entropy? It's also positive. Hope everybody sees that. And let me, I don't have enough room here for the last one. I'm gonna clear this up. So let's look at the, we're doing the aqueous. Notice that I don't care what the molecules are themselves. I care about the state of those molecules and the matter, how much matter, the amount of matter. Aqueous, and then it becomes aqueous. So everybody is aqueous. So let's look at the amount of matter. We have 1, and then we have 2, and then we have 1. So we went from 3 to 1, from more to less. More chaos to less. What does that mean? That the change of entropy was negative for this reaction. Okay? If this doesn't make sense, please email me and we can talk about it, or ask questions when we have our Zoom meeting. Now, we're gonna the second section of this module is about having a quantity associated with entropy. So not only deciding if it's a positive or negative, if it's gained, chaos, or lost. Okay, we need to be giving it a quantity, a number. We're going to use table 13.3 on page 444 in your textbook to use this equation to calculate the change of entropy at standard conditions. All substances, even elements, have absolute entropy. They exist, they have chaos in them. Okay? So the summation, again, you're adding up the entropy of the products minus the summation of the entropy at standard conditions for the reactants. Things you need to notice on the table. The table looks tiny bit different than mine because I don't have the exact table to put in here, but what you need to notice is that the units are in joules per mole divided by mole and Kelvin, not kilojoules but joules. It's less energy. That all the values are positive, because the table is not for changes of entropy, is for entropy at standard conditions for different substances. And we know that all substances have some level of disorder. They exist. Let's look at extra practice problem number 8 on page 581. So what are we needing to do with this? Let's look at an example. It says if the standard absolute entropy of oxygen gas is 205 joules divided by mole and Kelvin, what is the change of entropy of the reaction in problem number 7? So let's try to solve this for a second. Let me copy the reaction in number 7 for a minute, okay? Hey, let me erase this for a minute. Copying it wrong. For ammonia gas, add oxygen to gas, for nitrogen monoxide gas plus 6 molecules of water gas. And it says if the standard absolute entropy of oxygen, so for oxygen, the entropy for that oxygen is 205.0 joules divided by mole, and Kelvin, what is the change of entropy for this reaction? Remember what that was? That was a summation of the entropies at standard conditions for the products minus the summation of all those entropies for the reactant side. So that means you have to go in and use table 13.3 on page 544 to find those standard entropies for the different players here. So let's see. Change of entropy is, what do we have here? The products. There are 4 of them for these. If you go to the table, you'll find out that for nitrogen monoxide is 211, and they are joules mole per Kelvin. I'm not going to put it there because I don't have a lot of room, but you should. Plus, there are 6 of the waters, and I'm going to add it to my previous one. So, because it's a summation, 189 for each one according to the table, and I'm going to minus the reactant side. 4 for the ammonia. I find ammonia on the table, 193, and I add that to 5 of the oxygen, which were given to me, 205.0. put everything in the calculator, and I come up with 181 joules mole Kelvin. And this is my answer. This is a positive entropy, which is great. Okay. That's the kind of problems that you need to be able to solve with this table and that equation I just showed you a minute ago. Okay. To predict if a reaction is spontaneous or not, we are going to be using what's called Gibbs free energy, abbreviated by G by G. That's Gibbs energy, okay? Gibbs free energy. So we're going to calculate the changes in Gibbs free energy using this equation. It uses enthalpy and entropy and temperature. Both enthalpy and entropy and the temperature are responsible to decide the fate of a reaction, if the reaction is going to happen or not. There are some reactions that are endothermic, so require a lot of energy to get started. That will not happen just at room temperature, but if you light it, if you put a flame underneath, increase the temperature, they will go ahead and run. Okay? So all those players decide if a reaction is going to be spontaneous or not. So here you have it. A change in enthalpy is not the only factor to consider in predicting if a process is spontaneous or not. We need to also take into consideration the entropy and also the temperature. Now, you're going to have to memorize this equation. So the changes in Gibbs free energy in joules or kilojoules, okay, one or the other, is going to be the change in the enthalpy that you know how to calculate minus the temperature that we give the reaction times the entropy, the change in entropy for that reaction, which you know how to calculate as well. And this you need to memorize as well. If the change in Gibbs free energy is smaller than 0, so it's a negative number, the reaction is going to be spontaneous. So it's consistent with the second law of thermodynamics. The universe is happy. If the change in Gibbs free energy is bigger than 0, a positive number, the reaction will not take place because it would violate the second law of thermodynamics. Here you go. So both are taken into consideration to decide if a reaction is going to proceed or not, spontaneous, if it's going to happen or not. So by looking here, if your enthalpy is positive, your entropy is negative, so it's losing chaos, which is not good. But the combination is positive because probably that's negative times negative, okay? Then the change in Gibbs free energy is positive, and by definition that means it's not spontaneous or non-spontaneous. Another combination, enthalpy is negative. What does that mean? It releases energy. So this was endothermic, this is exothermic, it's releasing energy, losing energy. And now here the entropy is positive, entropy, the chaos now is gaining chaos. The combination with the temperature is negative, and now it's negative. This has determined, Gibbs free energy determines the reaction to be spontaneous. The other combinations give a Gibbs free energy that can be positive or negative, so it all depends on the temperature. So if you have enthalpy negative, entropy negative, this now is positive because negative times negative is positive. it all depends on this, the temperature. At low temperatures, spontaneous. At high temperatures, not spontaneous. And the same thing here. Okay. So take into consideration this table, and this is another way of saying the same thing. Okay, exactly the same. And you have it here. You can look at it if you want to. I put different ways for different people's brains think differently about things. So whichever table works for you. Now, Gibbs free energy is also a state function, and if you remember what a state function was, it's a function or a value that is independent of the process in which you reach that value. Okay? The beginning and the end is what is important, the fact that you reach the end. So we can use Hess's law to calculate the changes in Gibbs free energy at standard conditions using table 13.4 on page 447. Good for us. By using this equation. The change in Gibbs free energy at standard conditions is the summation of change of Gibbs free energy is a mouthful, okay? At standard okay, sorry about that. Here we go again. So the change in Gibbs free energy at standard conditions is the summation of that for the products minus that the Gibbs free energy, it's a mouthful here, for the reactants. So keep this in mind. You need to memorize, and we need to be able to apply it. If, and this is also other things you need to memorize, the Gibbs, if we're looking at the change of Gibbs free energy of formation at standard conditions of any element in its elemental form is 0. So we can disregard elements. Anytime that you're working on a reaction at a temperature other than 298 Kelvin, remember this is standard, 25 degrees, you need to use this other equation. Okay? But if you have standard is 25 degrees and 1 atmosphere, remember, then you can use table 13.4 on page 447. Okay. Things to notice on this table, and that is on page, and once again, mine doesn't exactly look like yours, but look at your table. Things to notice. We're talking about standard conditions, 25 degrees or 298 Kelvin and 1 atmosphere. And you have values in kilojoules per mole. Okay? And you only can use this table if you are at the standard conditions we mentioned before. If not, you have to use the other equation. Okay. How? Let's look at all of these using a problem. Example 13.7 on page 448. In example 13.3, we studied the following chemical reaction. To give it to you is balanced grade, and found that the change of enthalpy was minus 114.2 kilojoules. If its change of entropy is minus 147, remember that negative means what? Is losing entropy, which is not what the universe wants, okay? And this is joules moles per Kelvin. What is the change of Gibbs energy at 532 degrees Celsius or 805? So this is not standard conditions. We're not going to be able to use the table. Okay? Is it a spontaneous reaction at that temperature? Okay, that's the first question. Is there any temperature at which the above reaction does become spontaneous? And here it says, what is the Gibbs free energy of the following reaction at 298 Kelvin? Ooh, that's standard conditions. Is it spontaneous? And then we're going to do one extra more. So let's break this into pieces. Okay, so we're doing example 13.7, page 448. Okay. Now, first section. They want you to calculate the change of Gibbs free energy at 532 degrees Celsius or 805 Kelvin, whatever you need to use, you have to decide. Well, our formula, because we cannot use the table, looks like this. This is the only formula we can use, okay? So do we have what we need? Well, this we calculated in the previous problem. This is given to us. We have the temperature as well. The only trick here is that the units do not match, okay? Look at this. The change in enthalpy was minus 114.2 kilojoules. Sorry guys, another interruption, phone interruptions, but here we go. We're gonna finish. I was saying that the units do not match, so you needed to notice that the change here that was given to us was minus 147, but it had a joules per mole per Kelvin. Okay, I noticed that there's a Kelvin here, so I'm gonna use my Kelvin temperature. Okay, so the first thing I need to do is decide, am I going to use kilojoules or joules? I'm going to use kilojoules, so I'm going to change this into kilojoules. Okay, how many joules are in a kilojoule? There's 1,000 joules in 1 kilojoule. Now my joules are gone. I'm going to be left with kilojoules, and that's going to be minus 0.147 kilojoules per mole per Kelvin. Great. Now I have everything I need, and I just need to put it in the formula. That's all I have to do. Let me erase these now that we have seen this section. So the change, or the change in Gibbs free energy equals, I'm gonna write it again. Okay, so equals minus 114.2 kilojoules per mole, great, minus the temperature, I'm going to put brackets, 805 Kelvin, that's multiplying, we just change this into kilojoules, minus 0.147 kilojoules, mole, and Kelvin. Okay, sorry, it doesn't finish very well, but it is what it is. So you come up with 4 kilojoules per mole. What does it mean to be positive? Positive, remember, if the Gibbs energy, you're going to have to memorize this, is more than 0, positive, it's non-spontaneous. Okay, so the first section is answered. Is it spontaneous? No, it's not. But it says, is there any temperature in which you could make these spontaneous? Okay, this is the second section for this problem. Let's erase these. So what do we want? We want the Gibbs energy to be smaller than 0. That will make it spontaneous, correct? So if we have the Gibbs energy, which is enthalpy minus temperature, change of entropy, be smaller than 0, it will take place, it will be spontaneous. What temperature makes this happen? Well, we need to isolate that temperature to find out when that happens. This is algebra, and before I get started with this, I want you to remember that if we need to multiply or divide both sides by a negative number, we're going to have to switch directions of the inequality sign. This is algebra. That's all it is. Okay? So let's put information in there. What do we have? We have minus 114.2. Just going to put the numbers for right now. Okay. Minus t, which we don't know, and then the other number is minus 0.147, is to be smaller than 0. Okay, so what do we have? this has become positive now. I hope you see that. Negative times negative. And this goes on the other side being a positive. So we have 0.147 temperature has to be smaller than 114.2. Okay, great, very good. So we can now put this number on the other side dividing. This is algebra, 0.147. So the number here comes out that the temperature, if that temperature 777 Kelvin, or any temperature that is smaller than 777 Kelvin, this is going to be negative and it's going to make it spontaneous. So a temperature that's smaller than 777 Kelvin will make it spontaneous, and that's your answer. Okay. Now, the last section here says, what is the change in Gibbs free energy for the following reaction at 298 Kelvin? Remember that these is standard conditions. They give it to you. The reaction, this is a solid plus 2 HCl equals, and that just means that we're going to be able to use the table. This is a solid and this is a gas. So we're going to be able to calculate this, correct? And what does it look like, that formula? The formula looks like this. You need to sum of all of those information for the products, and you have to sum and minus it for all of them. Gives free energy of formation at standard conditions for the reactants. Great. So I'm going to put colors here. The products are these, and the reactants are here. We also know that we can, anything that is an element can be by itself, can be disregarded as 0. So this is an element, and here we have another element. So those two are going to be able to be disregarded. So let's start with, by looking at the table, go back to page 447 in your book and find table 13.4. That's what you need to be able to, you need to use that table to be able to do this problem. So products, we have 1, and according to the table, the value for calcium chloride is, maybe I should just put it like this, minus 750 kilojoules per mole. Great. Now we have to minus the reactant side, which is hydrochloric acid. How much of that do we have? We have 2, and if you go to the table, you'll find that the number for that, this multiplication sign here, is minus, the value is minus 131 kilojoules per mole. This is all coming from the table, okay? So I put everything in the calculator. Put it in the calculator and I come up with this value, minus 490 kilojoules of energy. So what does it mean to be negative? To be negative means that this is less than 0, and that makes it spontaneous. It's a spontaneous reaction. So let's do an extra practice problem, number 9. Let me see if I can just give you the value, and if you get it right, just move on, and if not, check to see how it's done. Let me see what it asks. I think maybe there are 2 sections to this. No, they want the temperature in which is spontaneous. The answer for that, number 9, the temperature has to be smaller than 5.46 times 10 to the 3 Kelvin. So if you got it, just move on. This is a video. If you didn't, check to see how this is done. Okay? So let's see. The problem reads as follows. If the change of enthalpy at standard conditions of a reaction is minus 623 kilojoules per mole, and I'm going to put it here, and the change of the entropy equals minus 114 joules per mole per Kelvin, what is the temperature range for which a reaction is spontaneous? Well, the first thing I need to notice is that the units are not the same. Okay? Please notice that kilojoules versus joules, that's going to be a problem. So the first thing I need to do is make sure that I change my joules into kilojoules. So minus 114 joules per mole Kelvin. 1,000 of them is 1 kilojoule. So this right here is the same as minus 0.14, which we did before, just the same number. Kilojoules, mole, and Kelvin. Great. Okay, I'm gonna change this so I can have some room. Minus 0.114 kilojoules, mole, and Kelvin. Now they are all in the same units. So remember that for a reaction to be spontaneous, this has to be true. Okay, it has to be a negative number. So if you remember the formula looks like this. Okay. So we want this to be negative. So we want to know at which temperature this happens. We're going to put the values in. So let me erase this, copy it again, so we have a fresh copy. And now we're going to put the values in. I'm not going to put units for right now. Minus 623 minus the temperature multiplying minus 0.14 has to be smaller than 0. Let's move on. This goes on the other side. So that becomes positive. Minus times minus. So 0.114 multiplying the temperature. Positive 623. So divide everything, 623 by that 0.14, and that's where you get that it has to be smaller than the 5.46 times 10 to the 3 Kelvin, and that is your answer. Any temperature in which this is true, the temperature is smaller than this value, it will be spontaneous. So that's the kind of problem you need to be able to solve. And this completes the second half of Module 13. Read the textbook, add to your notes, review examples if you need to, do all on your own, correct them as you encounter them so you don't make the same mistake over and over, study for the quiz. No labs this week, no labs. Review questions, self-correct. Practice problems, use the answer key first, try again, and then check to see how it's done if you still don't get it. Please ask me questions during the week, and then I'll see you on Friday for our Zoom meeting. Have a good week.